All right, this is Bruce demonstrating Lab 7, which involves implementing an item-based nearest neighbor collaborative filtering algorithm to 3 datasets provided by the professor. My partner Alejandra won't be presenting with me today. She was unable to be there for demonstration, so it'll just be me. But yeah, we've made the decision to implement this assignment in Python since it involves messing around with tables of data, and we thought it would just be a really good idea to use Python's NumPy library, which helps with some of the calculations when tables and matrices are involved. So the libraries used are NumPy and Pandas. Pandas is just used to display the final matrix, the resulting matrix with the predictions. So first, I will run the program and show you what I have. We'll be running the first test with test.txt, the first input. So if I hit run all, we get our results all the way at the bottom. Over here, we can see that the user 1, Alice, has not given a rating for item 5, and over here, indicated by -1, and we've been able to predict a rating of 4.65 for that user. And if we double check with the output, it is roughly accurate, 4.65. We'll move on to test 2. And if I run all, we do fill in some of the predictions. And over here, the users that have not entered any readings is kind of given at a diagonal. And if you compare my output to the output given by the professor, we have I have 3.8, the professor has 3.47, I have 2, 3, 3, 2, 3, 2, 3, 3, this is 2.9, so I guess this is rounded up, and 1. The only difference here is I have kind of, the reading my algorithm has predicted is slightly higher, and I'll talk about reasoning as we move on. So, but let's look at test 3, and this is where some of the predictions are a bit different than what the professor has given. So if I hit run all and I look at test 3, so here we have multiple missing readings amongst items, particularly at least 2 per user, and there's at least 2 users who have not rated items. And if you compare my results with that of the professors, we can see that some are very similar, but some are not. So for example, the first reading given by Alice, I've predicted a reading of 3.01, whereas the professor's is 3.45. However, for item 6, my prediction for Alice is 3.23, which matches the professor's 3.23 right there. So that's 1, 2, 3, 4, 5, 6 for item 6. And we have something very similar. Over here, the professor has given, well, user 1 has rated item 2 3.21, whereas my prediction was 2.41. For user 2, we have 2.91, and I have, this is user 2, so user 2 right there. Item 3, I've also got 2.91, and yeah, so I think that's so in this test there are a few more differences between the predictions my algorithm makes to that of the professor's. I'll explain why I think so right after I demonstrate the final input, which is test A. So if we clear all output, run all, there we go. So test A right there. So test A, the Alice has not rated item 5, and user 2 has not rated item 1. If we compare the outputs, so output test A, here we get 4.6 for item 5 and 4.4, slightly off. So the professor has 4.45, I have 4.40. So there you have it. For test 1, 2, and for test A, my predictions are more or less accurate. It is just for test 3 that some of the predictions do differ. I'll walk through the code. So first off, we import necessary libraries. Pandas is only for the last bit over here where I get print the final results, just so that it looks a bit nicer. So we have rows and column headers, and NumPy for matrix multiplication, and just to use ND arrays. So the code starts right here. So we first create an empty array, and then we grab all the text from the text input files, and then we just splice the text. We split the text for headers, users, and content. Once that's done, we try and initialize and kind of clean up the matrix. So that's done by this function right here, initializing init ratings matrix, which is defined right here. So for this, we go through each line in content, and we just clean some stuff up. So first we try and replace all the negatives 1s to 0, and then we convert everything from 0 to NPs. NumPy is not a number, a data type. The reason why I do this is so that it's more easily recognizable when something is missing in the matrix. So in order to signify that a rating has not been given. After that, I subtract the mean from that array. Before I talk about that, actually, here I print out each of my results, and we can see that after initializing the matrix, this is what it looks like. Very, very similar to what we have. If I go back to, we were testing, yeah, test 8 right there, yeah. So we have very similar inputs right here. This is just a 2D matrix. I'll be working with 2D matrix throughout this algorithm. And the user is not given a rating right here and here, which is very similar to this and this. So once that's done, in order to get the adjusted ratings, we have to subtract the mean from our initial matrix, and that's what I do using this function that I've created, subtract mean. From there, we get the average vector and the adjusted ratings. The average vector is necessary because after calculating all our predictions, we want to add that average back to the matrix so that we can actually make accurate predictions. So if you look at our mean function, what I do here is excuse me, I convert all the not number data types to a 0. So when I'm calculating the mean, it does not take that into consideration, and I just subtract. I create a vector of the averages, and then subtract that from ratings, and return that subtraction as well as the average. That looks something like this: a one-dimensional vector of averages corresponding to each item, each user row. So for example, in this example right here, 4 is the average, and we can see in the next we can see right here that 4 has been subtracted from from the first row. So 4, 0, 4, 0, 3, -1, and 5 and 1. So that's pretty accurate. Our adjusted ratings are appropriate. And finally, we try and compute our similarity matrix, and we feed in the adjusted ratings matrix, which is this right here, and the cosine similarity function returns a 5x5 matrix, 5 items, 5x5 because there are 5 items, and yeah, of negative and positive scores depending on the similarity. And this is where I feel that my code isn't the most accurate, just because I know that my code does consider readings that have not been given by specific users. So it doesn't take that into consideration when computing the cosine similarity, but I feel like something else is going wrong. So over here, what I do is I create an empty array, and then I go through the adjusted matrix twice. I transpose it, so in order to just convert all the columns into rows rather than vice versa, just for simplicity. And first I calculate the prediction. I grab all the positions that are that have all the ratings that have not been given. I grab the positions of them. Once that's done, I convert each one of those. I convert that specific row, each not a number, to a 0. This would kind of not allow the matrix multiplication. When we multiply the matrices, it would help disregard those values. And for each one of those predicted values, I throw in a 0. Once that's done, I create a row of empty zeros, and then I go through the array, the whole matrix a second time. Once that's done, I convert that as well to any inputs that have not any ratings that have not been given. I convert that to a 0, so it does not get considered. And then I kind of do that again over here for each predicted position. And then I compute the cosine similarity. So I do a dot product of that specific row to the row that we're trying to compare to. And then I normalize each one of them and multiply and divide. And then I just store that similarity in that value in its corresponding row in the empty row. And once it's done, gone through the matrix once, I append that row to my empty matrix, and then go to the next row, and then go through every matrix as well for another time until we have all our scores. So that's my cosine similarity calculation. Initially, I knew that Python has a few libraries that does this for you, and I intended to use that, but unfortunately, and that was actually the main driving factor of using Python, but unfortunately I could not find a specific function, or I wasn't able to manipulate Python's cosine similarity functions to kind of disregard or consider ratings that have not been given. But this is where I feel that my code goes a little bit wrong. But once that's done, it does give us similarity scores that are pretty accurate. We can see that over here there is a diagonal of 1s. That's because each over here, for example, this row would be item 1, and this column would be item 1, and if the similarity between them is 1 because it is the same item. That's why we have a bit of a diagonal of 1s. And finally, for predictions, this is where I code in the number of the nearest neighbors that I want to consider. This can be changed in order to kind of increase or decrease the nearest neighbor calculation. And then I go into trying to make my predictions. I iterate through each user in my adjusted ratings matrix. I grab the predicted positions, and once that's done, I grab the position. I zero the positions of each user, which essentially any ratings that is not a number, I put a 0 there. And then once if there have been ratings that are not given, I iterate through those positions. Once that's done, I then take the similarity matrix and replace any. I take a row from the similarity matrix and replace any negative with a 0. And then right after that, I replace the predicted positions in the similarity with a 0. So the item we are trying to predict for will be 0 when comparing with the same item. And after that, I try and sort the similarity matrix so that I can grab the top k nearest neighbors. I do this by converting into dictionaries in order to keep its indices in check, because I use the same indices over here to grab its corresponding ratings. Once that's done, I call npSum, and sum, first I multiply the similarities with the final ratings, since I just do a dot product of that, and then sum the results. And then for the denominator, I sum all the similarities that I want, so the top case similarities. And then for the prediction, I just divide the numerator and the denominator, and I have a prediction. And then I manipulate the adjusted ratings in a matrix that I've inputted into this for loop, and I throw in the prediction. So that's how I make predictions. One thing that I'd like to say is that this conversion to dictionary and sorting it would have been a lot better if I had used pandas data frames, because pandas data frames do help you keep track of indices with column headers and row headers. So that would have been a lot more easier and a lot more efficient, because over here we're calling a sorting algorithm, we're converting it to a dictionary, we are converting converting it again to a dictionary, and converting it back to a list, which is a lot of computation. Even over here, we are converting a couple of objects to list objects. So this does have a lot of computation, require a lot of computation. So it would have been better to use data frames. But once that's done, we do get our adjusted ratings with predictions. But finally, we add back the average vector that we computed before in order to get the appropriate predictions. Once that's done, we convert that into a data frame, and I go ahead and I print it. And that's how I get my results. So things that I could have made better, one would be using pandas data frames in order to keep track of the indices. That would have helped a lot. Another thing is I could have used SciPy learn, sklearn or SciPy to sklearn and SciPy cosine similarity functionality to compute the cosine similarity rather than creating my own algorithm, just because it's probably a lot more efficient and it would improve the speed of my application. But yeah, that's my application. I know that my one of the output 3 was a little bit off, but if you do see an issue with my code, I'm 100% sure it I'm 100% sure it has to do with my cosine similarity function. If you do see an error in my code, that would be awesome. But thank you very much, and please give me good marks. Thank you.